How many words can be formed using the letters of the word machine if the vowels may occupy even positions and odd positions? So here we are given the word machine. If we look at the vowels, then there are three vowels as we can see, that is A, I and E. Now let's consider the first sub question, that is the vowels are to occupy the even positions. Now let's denote the even positions by boxes and the odd positions by the dashes. So since it's a 7-lettered word, we can see that there are 3 even positions and 4 odd positions. Now let us fill up the even positions with the vowels. So as there are 3 positions and 3 vowels, say first position can be filled with any one of the 3 vowels, the second can be filled with the one of the remaining 2, and the last one has to be filled with the last remaining vowel. So therefore in all there are 3 into 2 into 1, that is 6 ways to fill in the even numbered positions. Now in the remaining odd numbered positions, we have to fill in the 4 consonants. So as again we start distributing the consonants, the first place can be filled with 4 ways, the second place can be filled in 3 ways, the third in 2 ways, and the last one in any one of the ways. So therefore the total number of ways to fill up the odd numbered positions is nothing but the product of 4, 3, 2 and 1, which turns out to be 24. So as we want odd numbered places as well as even numbered places, we must do the multiplication of the number of ways in which they can be filled. So therefore that turns out to be 24 into 6, which is 144. So that's the first part. Now let's consider the second possibility, in which the vowels are supposed to occupy only the odd numbered positions. So now let's denote the odd numbered positions by the boxes and even numbered positions by the dashes. Now here if we see, there are 4 odd numbered positions, but there are only 3 vowels. So therefore we do not know in which of the positions 3 vowels will go, and in the remaining position clearly 1 consonant has to be present. So therefore let's count the other way around, that is, if we think about the even numbered places, they are definitely going to be occupied by the consonants. So let us count first the even numbered places. So say first place can be occupied by any one of the 4 consonants, and the next place can be filled by any one of the 3 consonants, and the other one, last one, by any one of the 2 consonants. So therefore the total number of ways to fill up the even numbered positions is the product of 4, 3 and 2, which turns out to be 24. Now if we see the odd numbered places, which are 4, and they have to be filled with 3 vowels and 1 consonant. So in all we can now think of them as just 4 letters to occupy the 4 positions. So that can be done in 4, 3, 2 and 1 ways respectively, as we have seen in the previous examples. So that turns out to be once again 24, and hence finally we will once again do the product of 24 and 24, which gives us the total number of words that can be formed. So that turns out to be 576. Now let's move on to the next question. Here the question is asking how many 4-lettered words can be formed using the letters of the word daughter if each word is to include the letter G. Once again let us designate the 4 places. Now here it's given that the letter G has to be present in the 4-lettered word. So that means the letter G can occupy any one of the 4 positions. So we know that there are 4 ways to do this. Now in each of these ways, that is, let's say assume that the letter G occupies the first place, just as an example. Now the remaining 3 places have to be filled with the remaining letters, and if we count the total number of letters in the word daughter, they are total 8, and one of the letter is G. So therefore these 3 places have to be filled with the remaining 7 letters. Now if you start filling up the places, that is, say one of the place can be filled with 7 letters and the next one can be filled with 6, and hence the last one can be filled with 5. So therefore that's what we do here. 7 into 6 into 5, and we have to multiply by 4 because G can occupy any one of the 4 positions. So therefore the final answer is the product of 4 into 7 into 6 into 5. That turns out to be 840. Now there is an indirect method also to calculate this count. That is, the required number of ways are nothing but total number of words that can be formed using the 4 letters of the word daughter, and from that we subtract the number of words in which G is not present. So therefore from that we subtract the total number of words without G. So therefore that will naturally give us the required number of words. Now how to do that? Suppose we want to count the total number of words that can be possible to form. So here let's once again denote the 4 places. The first place can be filled with 8 letters, any one of the 8 letters, and 7, and 6, and 5. So therefore total number of ways are nothing but the product of these 4 minus. Now if we consider the total number of words that can be formed which do not have G in them, so therefore effectively we have now only 7 letters with us, and using that we have to form the 4 lettered words. So therefore here, say one of the place can be filled with 7 ways, the next one with 6 ways, then 5 ways, and the last one with 4 ways. So the product of these numbers give us the number of words which do not contain G. So hence the final answer is nothing but the subtraction shown here, and as you can see 7 into 6 into 5 can be taken common from both, and hence the remaining terms in the bracket are 8 minus 4, which is nothing but 4 into 7 into 6 into 5. As we can see once again that is same as the previous answer, which is 840. Now let's move on to the next question. Now here there is a case of a letter lock consisting of 3 different rings, each having 5 different letters. What is the maximum number of false trials to be made before the lock is opened? As we know, we must have seen the combination lock on suitcases, which has a different rings which we can rotate and bring in one of the combination of letter to try opening of the lock. So if we show that by this simple diagram, that is, let's consider that there are 3 rings as mentioned in the question. Now, each ring consists of 5 letters on it. So I'm showing here 3 rings with 5 letters each, and by rotating or turning the ring we can bring in one of the particular combination. So therefore one particular combination represents 1 trial. So the question is asking what is the maximum number of false trials. So here the false trial means it's the combination of the letter which will not open the lock. So what is the maximum number of false trials before which the lock is open? So first of all, if we count total number of letter combinations, so that is total number of letter combinations. That can be done by using the principle of multiplication. Now, as we know, for each ring there are 5 possible characters that can be brought. So therefore here if we think about finding out how many total number are there, so that is nothing but the product of 5 into 5 into 5. So that turns out to be 125. 125. Now we know that out of these 125 combinations, one of the letter combination is going to open the lock. So therefore all the remaining 124 are the wrong combinations. So therefore if at all there is some thief who steals this particular object with the lock, the total number of attempts, maximum attempts that have to be made are nothing but 125 minus 1. So that turns out to be 124. So therefore the question is asking us the total number of false trials, which is 125 minus 1. It is 124.